Welcome to the APL Quest. See APL Wiki for details. Today's problem, the 8th from the 2015 round of the APL Problem Solving Compensation, asks us to replace instances of the number 13 with the number 12.99, but only numbers, not where it's written in text. However, while the test cases given in the automated testing system on problems.tryapl.org only are fully numeric flat arrays, by extending the domain, we can get quite some depth to this problem. Without further ado, let's get started. So let's start with a very simple test case, the type of test cases that we might see in the automated testing system. And for this, we can use a mathematical approach. So we can say the argument minus 0.01 times a Boolean mask for the argument. So here, this will give us ones where there are 13s, and then we multiply with this, which is the difference that we need to make when we have a 13, and then we subtract that from the argument itself, and that works fine for arrays like this. However, if we take it very literally, what it says in the problem specification, that we only need to concern ourselves with data that are numbers and not 13s that occur in text, that would seem to indicate that there could be text. So let's throw in some characters. So this is a flat array still, but it's mixed type. And of course, this is not going to work very well when we try to apply the f function on it. And that is because we are trying, while we can compare to 13, and that will give us 0 for the D and the E, we cannot subtract 0 from D and E. So we get a domain error in this case. And we had to go with an entirely different approach. So let's write a different function here. And one way we can do this is to use selective assignment to change the value, or we could use modified selected assignment to do the subtraction. For that, we need a variable which we are allowed to change. The omega in a defin is a constant. We're not allowed to change that. So we'll take that and we'll use the name r instead. And we don't need this value right away, so we'll defer that. Instead, we want 12.99, and we want to put that into R, but only into a subset of R selected by the mask where 13 is equal to the argument. Or we could put R as well here. It would give the same result. Now that R has been updated, we just need to ignore the result of this assignment, which would be 12.99 anyway, and then return R. And G can be used on this variable, and it just ignores the D's and E's, and even the 11, because we're only interested in elements that are 13. Okay, what happens if we change things up a little bit? Let's take these numbers and letters from B and make them into a matrix instead. So now we've got a matrix with numbers in one column and characters in the other column. And if we try to use G on this, then we get a rank error, because we cannot use compress with a matrix left argument. It has to be a vector, a mask over the columns or elements in this case. But we can, of course, fix this. So if we take this G and make it into an H, and then we ravel the argument values first, then we are sending to the raveled argument, and then, but we didn't actually ravel the array R, and then we're returning that there. So let's try that H and C, and that works as well. But we said text before, and that might be even more than this. Before we go there, let's just see another way of doing this, which is very similar in what it's doing, but much more concise. And that is to use the at operator. So really what we're saying is that not considering the shape of the argument, we just want to replace with 12.99 at the positions where 13 equals that. And that's exactly what the at operator does. So we can write 12.99 at where 13 equals the argument. And that's all we need to do really. And that works as well. Okay, back to the text. Text, of course, can be more than a single character. So let's have a new array, which again, let's stick to a matrix so that we make sure that we don't have any regression on that. And this time, we're going to use a character vector as one of the elements. So it looks like this, a nested array this time, because one of the elements in the array is itself a vector. If we try to apply this function I on D, or for that sake, if we were to try to apply H, which works exactly the same way, then it's not going to work. I would give us this, and H. See, we get a domain error here. And that is because when we're doing this comparison, we're creating the Boolean mask. And so we said 13 is equal to the argument on D, and equal is a scalar function, which means it penetrates into all structure. And so we get an array of the same exact structure, but with Boolean values inside. However, such a nested array is not a valid argument, not for replicate, and so not for that operator either. So what can we do about this? Well, one thing we could do is not to use equal, because we don't want to penetrate instead. We don't want to penetrate into the arrays. So if instead we look at whether these elements individually are members of 13, that would consider them as a whole. So we have a collection, which is just a single element, 13, and then for each element in the argument, we look at whether or not they are members of that collection, you could call that single element. And then we can see we get an array of the same shape as the argument, and it doesn't penetrate into all that structure. So if we modify our I function, just changing that one little bit, then we're able to use our function successfully. Okay, but let's complicate matters even further. So we had D here with a character vector, which as one of the elements. But let's say we have a more complex structure. So we have still a matrix, and still the same elements. But this time, we bunch together these two elements into a single element. So there are actually 3 elements, and we're going to reuse the 11 because we need a 4th element. So we can see that here. And now the 13 is hidden deep inside. So while we can use the function j here, it didn't actually work, because inside it had a look. Are the elements members of 13? And it said that the 2-element vector of DDD and 13, well, that's not a 13, it's a 2-element vector. But that kind of defeats the purpose, because we would want this 13 to be replaced. So one solution to this is to use recursion. We only want to consider the simple scalars and replace those. Now, simple scalars, they have a depth of 0. If we don't have a depth of 0, any other depth, then we need to recurse. We need to go one step in. So on each element, whether it's just a scalar enclosure or whether it is a vector or any other rank array, we go through all the elements in turn and consider them anew, calling this same function. Otherwise, which means we do have a simple scalar, there are only two cases. Either we've got a 13, in which case we replace it with 12.9, or we don't, in which case we leave it unchanged. Now we can apply the function to E, and we recurse through all the whole structure and replace the deeply hidden 13 with 12.99. We can actually use a method that we had before. This function h, we were raveling the data to find the elements so that we could use compress. And we could do exactly the same, but instead of raveling, we kind of do a super raveling, which is in list. Still, we're not changing the actual structure of this temporary variable r. We are just assigning to its corresponding completely flattened version. And the same thing, we're comparing 13 to the completely flattened data in R. And then we can, oops, I should have named this not K, it should have been L. That's better. And then we can use L on E, and that still works. Finally, there's actually a pretty neat trick that we can use in here, and that is to combine this ability to assign to the enlist of a variable with the neater notation of using at. So again, we make a copy of our argument, we enlist that, and then change 12.99's where we have got 13 equal to, well, we can write the way we've done before. Well, actually, I like writing 13 first, because it's more, I find it more idiomatic in APL to write what we're comparing with on the left, as I see functions as having a left argument, which is kind of parameter, and the right argument is the data. So I'll write it like this. And now we replaced all these values of 13 with 12.99, but we have it all flat, and we just need to stick it back into the structure it came from. So we're assigning this to the enlist of R, and then discarding that and returning R. And now we can finally run this, and that also works. So that's all for today. Thank you for watching.